Hi everyone, my name is El-Haj-Mahmoud, and the only thing you need to know about me is I'm what's standing between you and lunch. So let's try to make this quick. And this presentation is actually by my colleague, Jose Marino. Jose is in Cambridge, UK. He couldn't make it to this trip, but he's our ACPI and secure word firmware architect expert. So I'll pretend to know what I'm talking about here, but let's go through this. So this is a quick introduction into ACPI for ARM. So I realize a lot of people here are may already know this material very well. Some folks may be coming from a non-ARM background and they know ACPI well, but they may have not heard about or may not be aware of all the extensions to ACPI that are needed for ARM-based systems. So that's the focus of this presentation. So use it as educational material for your teams. I'm not going to go and explain what ACPI is here. I think this is obvious to everyone. But at a high level, what you need to understand is that over the years, ARM have been working with the UEFI forum, updating and adding ARM enablement, ARM architecture enablement into the ACPI spec, a lot of the times in an architecture agnostic way. So it's like creating new generic table or generic way in ACPI that are specifically to solve an ARM architecture problem, but they are not ARM architecture specific. But in addition to those changes in the ACPI spec that found their way over time, we also have a number of supplemental ACPI specifications that are published and maintained by ARM. They are cross-referenced from the ACPI specification. You will find the links on the UEFI website to point you to the specific documents on the ARM website. And that's what I will be covering today. One note here before we start is you may or may not be aware, but unlike on other architectures where ACPI and UEFI are not necessarily codependent, right? So in other architectures, you could boot legacy with ACPI, right? So no UEFI and ACPI. On ARM, ACPI depends on UEFI. So you cannot boot an OS in ACPI mode unless you also have produced the full UEFI system tables and runtime services, etc. So the first table I'll cover in a hopefully quick series of overview of different ACPI tables are the changes to the MADT table in the ACPI spec itself. So those are ARM architecture specific, but they are in the ACPI specification. So you will have their enablement for the various ARM interrupt controllers through the different structures that are related to the interrupt controller, CPU interface, the GIC-C table, the distributor and redistributor, the GIC-D and GIC-R tables, and the interrupt translation services, and ITS. And these GIC or the generic interrupt controller architecture comes from the ARM ISA as part of the ARM architecture, or rather not the ISA, but the system architecture extension. The GIC architecture started with version 2, and these are all supported in ACPI. Version 2 lacked MSI native delivery. We added that through what we call the V2M extension, which is defined in one of the ARM-based system architecture specifications. It allows you to get to do like an MSI delivery frame for the GIC V2. GIC V3 added native MSI support, so you need GIC V3 with ITS to support ARM systems in a standard way when you have PCI supported in those systems. And again, you will find that as a requirement in our base system architectures and our compliance check tests. GIC V4 was backward compatible to GIC V3, and it adds some of the virtualization enhancements. And finally, we have GIC V5, which is a newly introduced architecture that was just released. The ACPI ECRs are in progress. They are code first. We'll talk about these at the end. The second table that I want to cover here is the IORT table, right? So that is, I guess the closest would be the DMAR on Intel, and I forgot what the table in AMD is, IVRS, thank you. Too many acronyms. I'm more familiar with DMAR because I implemented that in the past. But so the IORT table describes the relationship between IO related subsystems. So you will have nodes there, different entries for different system components, the root ports, the SMMU, or the System Memory Management Unit, of an ARM specialized form of an IOMMU, an ARM architected IOMMU. You will also find entries for the interrupt controller translation services, some other generic named devices that could exist here, and so on. So this allows you to describe things like stream IDs and correlation between stream IDs and requester IDs and device IDs. Allows you to describe memory ranges. Think of the RMR, reserved memory regions, like that are described in the DMAR ACPI table. You can do all of that here in IORT. Very important, fully supported today in EDK2, although there is a lot of platform work that you have to do on every platform, and fully enabled in upstream and in Windows. The other table that is important to know about, mainly for servers, I guess, but this is the ARM Error Source Table, or AEST. This is a table that is part of the ARM RAS story, so it's published as part of the ACPI for RAS specification from ARM. That's a table that enables the OS to discover the error sources from hardware. So it's complementary to the API, the Platform Error Interface Framework that we are all familiar with, the RAS ACPI framework. You can think of this as it allows OS kernel first handling of RAS, right? Because you're giving the OS a discovery of the different RAS agents and the RAS nodes that exist within those agents. While maybe the API framework is more geared towards the firmware first handling of error, but the two work hand in hand. This is also done in EDK2 on a platform by platform basis. The patches took a long time in upstream Linux and struggled to land. I think there is some renewed interest in them, and they are under active review, I saw recently. So hopefully it's one of those chicken and egg, where's the hardware to test it, and we need the OS support before we can ship the hardware. But they are making their way, and hopefully they will be supported soon. Another feature in the ARM architecture is MPAM, Memory System Resource Partitioning and Monitoring. So it's a quality of service feature, allows you to, through a standardized way in the architecture, to do performance monitoring and specific partitioning for some subsystems. There is something called the Memory System Components, or MSTs, that are defined, architected, so they are defined by the ARM architecture, but they can be implemented outside the CPU. So if you have like a memory controller, for example, a memory controller can implement the MPAM architecture in hardware and present those MSC nodes, right? So the MPAM ACPI table describes some of the discovery of these components, right? Because like I said, they can be distributed in various subsystems in the SoC. One interesting thing there that we found it useful to define was a firmware-backed specification for MPAM. So this is DN01144. So it's not exactly ACPI, but you discover it also from ACPI. So ACPI can tell you these are the hardware-backed MSC interfaces that are available from the different components, and these are the firmware-backed MSCs. And with firmware-backed, if you have a piece of hardware IP that does not implement the ARM architected MPAM interface, well, you can implement the firmware version of that, which presents the same architected register layout right, that are not present in the hardware, but it presents them in a firmware interface. And then you can have a microcontroller, a service microcontroller that services that interface. Is implemented over the platform communication channel, the PCC, which is another ACPI concept that says here is a shared mailbox between a microcontroller in the SoC and between the OS. And one of the protocols that you can put over that standard mailbox is something that you can present the MPAM firmware-backed interface. The patches are actively being worked on upstream and finding their way to getting merged soon, hopefully. SDEI, Software Delegated Exception Interface. So that is mainly an SMC interface, a firmware, secure word firmware interface, but there is an ACPI table to discover the interface. That is an interface to allow privileged platform firmware, so firmware running in some of the secure words, including the EL3 root, to tell the OS to have event handlers, if the OS supports it, for certain types of events that are generated from the firmware. Very useful for example, firmware first RAS handling, right, to notify the OS back that and call a pre-established event handler, pre-installed event handler from the OS. This is mature. This is an old specification, and like I said, main use cases are in. There's some debug use cases as well, but mostly for the RAS firmware first handling. You'll also find a number of ACPI specifications that are now describing some IP-specific components from ARM. So everything I talked about so far are generic architected ACPI specifications. So whether you buy an IP from ARM or not, if you are compliant to the ARM system architecture, you will find the use, you will need those ACPI tables. These other specifications focus more on ARM-specific IP. So they describe standard HIDs and resources and sometimes static ACPI tables for things like the ARM standard generic watchdog timer or generic timer, or the ARM standard serial port controller. Or even the ARM CoreSight, like debug IP that you could integrate in your chip, or some other IPs from ARM. It's especially useful if you are integrating those IPs. There are some tables there that I feel are a bit more generic, so there is discussion whether those tables really belong in the IP-specific spec or in more generic ARM ACPI specs. One of those tables, for example, is the AGDI table. The AGDI table is a way to generate, it's the general debug interface. So it's a way to generate a non-maskable interrupt, right? That could be SDI backed or some other hardware backed. That feels a little bit more generic than something specific to the ARM CoreSight debug. So maybe that should be another location. But you'll find all of these are supported in EDK2 and upstream as well. A few other tables of interest that are in the ACPI specification, but are very ARM specific. In the FADT table, there are some flags that specify, for example, whether the power state coordination interface, PSCI, exists or not. There are flags to specify what are the conduit that's used to communicate with a secure word, whether you are on a physical OS or on a hypervisor, and you need to use the SMC or HVC, different ways of calling the supervisory firmware in secure word. There's a table called the PPTT table, Processor Properties Topology Table. That's generic, that's not ARM architecture specific, so other architectures can make use of it as well. It's in the ACPI spec proper. and allows you to describe topologies between the caches and the CPU cores. Very useful, especially if you have a heterogeneous mix of CPU cores like big, little, and different cache hierarchy between them, as well as the tables to describe the memory mapped ARM timers and watchdog timers in the GT-DT table. FFH is something that was mentioned earlier in Chris's presentation, Microsoft's presentation. So that's fixed functional hardware is a concept in ACPI that abstracts, some magic registers in the hardware. So you can access them from AML, useful, for example, on Intel-based platforms to read or write an MSR register, machine-specific register in the CPU, right? So for ARM, we extended the concept of FFH, added an operation region that describes FFH that allows us now to bridge ACPI, AML, to be able to call into the secure word through an SMC call, or more importantly, an FFA call like we saw in the framework that Microsoft presented earlier. So think of it as a standard interface bridge between ACPI and secure word to be able to pass a buffer of parameters and return values using that FFH. ACPI does not stop because the hardware architecture does not stop. So as the architecture evolves and the use cases evolve, we have to keep the ACPI up to date and catch up. GEC v5 is a new major piece of the architecture for the next generation of the interrupt controller. So ACPI proposals are already upstream in code first under discussion. The patches to enable the ACPI compiler, the ACPI CA, and EDK2 and Linux are all upstream as well, but not merged yet, as they'll be waiting for the ECR to get formally approved by ASWG. One side note, since the introduction of the code-first approach that Mark talked about in the keynote on Tuesday, ARM has found it very useful to go almost always through the code-first approach to publishing ECRs, so we can make them available to our ecosystem that are not members of UEFI forum. So they can work ahead on Linux implementations and EDK2 implementations and prepare without being gated by an ACPI spec to be formally published by the UEFI forum. So thank you to the UEFI forum for working through the nightmare of logistics and legal barriers to get that out, but that has really proved to be very useful over the years. Not exactly CPI, but related, SMMU driver. So EDK2 has this IOMMU protocol that allows you to use IOMMU during boot. That's currently not implemented for the ARM SMMU in a generic way that exists upstream. There is interest in enabling that and having an open source version of that in EDK2. I understand there is probably interest in other code bases as well, so something definitely to talk about. There is ongoing work there that's happening and some patches, so if there is interest in this, we can definitely collaborate, but we feel that this is a gap that probably should be filled for the community. And finally, the ACPI for FFA is very related to what I mentioned earlier. We had the FFH with the op region, and now we have the proper binding for ACPI FFA interface through that functional fixed hardware and op region and AML. And that's like I said, being used with the Windows improvements that we saw earlier. All right, I tried to go through this very quickly, so questions? Just remember we have lunch outside.
Real quick, we do have SMMU driver open sourced, and it should be getting upstream soon. I think we'd love to get feedback in any ARM vendor or others to provide help there.
Thanks, Sean. It's when you say open source, it's in Project Mu or in EDK?
Already, and it may have already been submitted in a PR form, or maybe not yet.
Okay, perfect. Yeah, thanks for the update. I was aware that there is some interest and work there. I wasn't aware that's already in open source. Thanks for the update.
Quick redirect on Sean. Are you aware of any fundamental core changes to accommodate that driver?
Yes, there's a couple different libraries for like non-discoverable.
Right.
And the DMA live where there's direct access.
Right.
So
Yeah.
there's a set of changes.
No, but also because in EDK2 there's like this one global IOMMU instance that, and on ARM you have like SMMUs all over the place. Was that an impediment for building this, or?
It was not. There is a single instance of this. It's basically routed through PCI-IO, like the IOMMU.
Okay.
So there wasn't, but we should talk about it.
Yeah. Thanks.
I guess this is really a comment rather than a question. All of these like supplementary specifications from ARM that live on ARM websites rather than being part of the main ACPI spec, I have observed that certain RISC-V supplementary documents have started popping up, looking nearly identical, but not identical enough. Could we start trying to push some of these things? I don't know if we can change history, but can we start trying to push more of new tables we add into more abstracted versions that go into the main spec?
As you saw from my presentation, that there is a lot has taken that path of generic tables. PPTT is a great example, right? I think already being used maybe by RISC-V or other architectures, LongArc. So there is definitely, that's definitely a correct approach. There are times where it's obvious that there are architectures ISA specific table, the DMAR, IORT, and IVRS. Thank you. I'm dyslexic when it comes to this. So there will be some ISA specific ones, and I'm happy it's one per ISA, not one per implementation. So there is that case. There's also the case of ARM IP specific tables and IDs, right? Is there still a room in or between all of these for things to become a little bit more generic and move to the ACPI spec? Probably, yes. So I say it's not all or nothing. There's a mix of all of these different types. Generic in the ACPI spec, generic that's in an ARM spec that could probably be candidate in the future to be ACPI spec, ISA specific, which could live in an ARM spec or the ACPI spec as long as we say it's an ARM ISA specific, and then ARM IP specific. There is a mix of all of these. Another feedback we heard is that there are too many specs. Let's try to consolidate. So that's definitely something on our radar of consolidating ACPI for ARM as much as possible. Whereas the other example that I saw was in confidential compute with the different approaches for confidential compute between Intel and AMD, and I expect ARM as well. So yeah, so there are places where we just can't avoid the ISA specific tables, unfortunately. But feedback taken and good point. I do want to add a comment before the next question. I just remembered that we also noticed that on the ARM ecosystem, as we are, I think the word that's used in the business side is democratizing silicon, right? Making it easier, lower barrier for entry for new silicon partners to productize things like our compute subsystem and through our ARM total design and other initiatives. So we find new companies entering this space that don't necessarily have a lot of firmware expertise. So a lot of what we know about UEFI and ACPI may be new to them, or they may come from other type of background of embedded or some other type of ARM-based devices, and now they want to build servers or some other mainstream devices that require these standards. So we are focusing more on educational material, practical guides of walking people through sample code and actual implementations and making it easier to digest rather than just pointing them to EDK2, right? Pointing to EDK2 is part of the solution, but it's not enough. So I was just reminded by my colleague Tom here in the back that we are working on a whole set of learning paths, like learn videos that are tutorials for UEFI and ACPI that start from the very, very, very basic, what is ACPI? At its very, very basic, all the way to, well, how do I customize IORT and integrate it for this specific IP implementation? And those should be available within a few months publicly on the ARM website.
Okay. All right. Thanks, Samer.